Okay. So, we had seen the working of a separately excited DC generator, but last class I had started on self excited generator. So, as I told you earlier, in self excited generator there is no field supply. No field supply will be given. So, whatever is the generated voltage, that itself has to give the field also a supply. So, what I am trying to say is, let us say this is my generator, here is the field. So, I am going to talk about this as RF. So, I am going to have the field current flowing through this. Now, if I want to connect a load, I can definitely connect a load here, but I would prefer to connect the load a little later. What I mean is, let us say I am going to have the open circuit characteristics of the machine is somewhat like this. Of course, the machine has to be driven at a particular speed omega by a prime mover. So, this is going to be my prime mover which is actually rotating this at a speed. So, this is my shaft. The shaft is rotated at a speed of omega by the prime mover. So, let us say this is going to be my EG and this is going to be my IF, and let us say there is some residual magnetism already existing in my machine. Even without the field current being of any magnitude, so IF is 0 at this point. When field current is 0, still I will have at least some amount of generated voltage. This voltage may be 10% or less than 10% or 5% let us say of rated EMF. So, rated EMF let us say is 220 or 200 volts. This is going to be of the order of about 11 or 12 volts. Now, this voltage is generated. Because this voltage is generated, that voltage manifests itself across the armature. Let us say this is A1 and this is A2. This is going to be about 12 volts to start with. This 12 volts is going to definitely pass a current through the field. Whether I like it or not, it will definitely pass the current through a field. Now, to get the magnitude of the field current, I have to basically draw the resistance line. So, the slope of this is going to be RF. When this is the current, I am definitely going to have, for this voltage, there will be a field current which will be corresponding to the magnitude of this line. Whatever the slope of this line, that is going to determine the field current. Let us say that is some IF1. Now, if I try to draw the OCC of this machine, maybe the OCC will be somewhat like this. This is going to be the OCC of this machine. So, corresponding to IF1, I am going to actually have a higher voltage generated. So, the voltage generated is going to be corresponding to this value. Maybe this is like 20%, or let me take some values directly. This is 12 volts. This may become as high as 24 volts. So, 24 or 25 volts have been generated. Now, corresponding to 24 volts now, this 12 volts have become 24 volts. Corresponding to 24 volts, I am going to have definitely a larger current. So, this was the excess voltage that was available. So, I should say IF-RF actually was only 12 volts. But corresponding to this IF, that is IF1, I have generated 24 volts. So, I have almost 12 volts in excess, right. This is available in excess. Now, that is going to circulate definitely a larger value of current which is corresponding to IF2, because of which I am going to have definitely a higher voltage being generated. So, the higher voltage that is being generated will be corresponding to maybe about 40 or 50 volts. So, I got 50 volts generated now. Now, corresponding to 50 volts, if I try to look at the field current, I am going to have a much higher field current. This field current is IF3. So, initially I started off with 0 ampere field current. Maybe it became 0.1 ampere. This will be probably 0.5 ampere. and this has become almost 1 ampere of field current. At 1 ampere of field current, I would definitely have a higher voltage generated, right. Maybe this is as high as 150 volts or 130 volts. Now, corresponding to this value of 150 volts, the field current has increased quite a bit. But look at this, previously I had an excess voltage of 12 volts or something. Now, I may have an excess voltage of 25 volts. Now, I am going to have an excess voltage of much higher voltage, which is actually 100 volts. So, this is corresponding to IF4. So, this current can be as high as, let us say, 1.8 amperes. Now, corresponding to this, I am going to definitely have a higher voltage, but please note, I have already attained close to saturation, because of which the voltage has increased only slightly, maybe 180 or 190 volts. Now, with this, when I go to a little higher value of field current, so let us say this is IF5, which is maybe 2 or 2.1 ampere, I would have reached maximum value of actually 200 or 220 volts. So, wherever this open circuit characteristics is intersecting with the IF-RF or load line of the field circuit, that is where I am going to arrive at really the operating point. So, this will be the operating point of the generator, where IF-RF will become equal to Eg. So, there is no excess voltage available at all. So, please note, the initial operating point was this, from that it went to a higher field current, from which it stepped up to this particular value. Then from here, so I can say this was the operating point P1, then it came to P2, then it came to P3, from there it came to P4, then it went to P5. From there it went to P6, which is the final operating point. So, the voltage is building up slowly because of the excess voltage that was available to circulate a higher and higher field current through this. That is the reason why the voltage ultimately reached this point. Now, once it reaches this point, we can actually afford to connect the load. That is when we are going to connect the load. So, this particular resistance value, this is a IF-RF line, I told you. So, the slope of this line basically is going to give me whatever is the resistance value. So, if I measure what is the actual slope of this line, this particular line which is tangential, this is known as critical field resistance or critical resistance of the field circuit. So, this particular slope of this particular line, or which is tangent to the curve OCC, I call that as the critical field resistance. If the resistance is below this, we can have voltage buildup. It should actually start from, yes, thank you for pointing out, it should have been somewhat like this. It should have started from the origin, obviously. Yeah, but the voltage what you are getting is minuscule compared to what you got in the residual magnetism. So, it is going to be really, really small. So, you would not have anything to write home about. That is what we are trying to say, basically. So, you are not going to have sufficient voltage coming up as the generated voltage when the resistance of the field circuit is greater than or equal to that of the critical resistance. So, I would say for the voltage build-up process, mainly 3 conditions need to be satisfied. 3 conditions to be satisfied for the voltage build-up process in a self-excited generator. The first thing is, unless I have a residual magnetism, it's definitely not going to work, because I'm looking at field current equal to 0. The field current raises from 0 value only because of residual magnetism generated voltage. So, for sure, I should have residual magnetism. So residual magnetism should be present. That is the first thing that needs to happen. The second one that I want would be, once the residual magnetism kind of generates some voltage, whatever is the current that is flowing, so we said that the current is flowing in this direction. If I say this is plus and this is minus, this is how the current is going to flow, right? So this current, what is flowing through the field circuit, should aid the residual magnetism. It should not kill the residual magnetism. So the current that is flowing in the field circuit because of the voltage that is being generated should aid the residual magnetism so that the flux builds up further and further. If it is not really aiding, it is rather opposing, the entire thing is suicidal, right? It's not going to really work any further. So I should have basically the field current that is flowing, right, should aid the residual magnetism, or the flux should build up further and further. If that does not build further and further, we are going to have a problem of suicidal operation of the generator. So the voltage will be killed, basically. And the third thing is, the resistance of the field circuit should be less than that of critical field resistance. So all these three things should be valid. Only then the self-excitation process really can, go ahead. I can also say that if originally my field resistance line itself is like this, I have got the field resistance line which is IF versus IFRF, which is indirectly EG, right? IF times RF, we are taking it as EG. So this is the field resistance line. By chance, if I am driving the generator at a much lower speed, if I am driving the generator at a very, very low speed, then also the intersection point will not be really good enough for me to get any perceivable voltage. So if I am already given the field resistance line, I should be able to draw the OCC for this particular generator. Maybe I had drawn it at a particular speed. I can bring down the speed further and further, and I should be able to say, for this field resistance line, if I go below this particular speed, I will not get really voltage build-up process possible. So if I try to draw it, for example, in the previous page, so I had drawn this as the resistance line first to start with. So maybe if I had had the OCC at another speed, maybe, right? So that may be really giving me, much lower value of voltage which will come up for this particular generator operation. So I may not be able to really see any proper voltage, right? So this will be even more visible if I try to choose the resistance line probably somewhat like this. If it is at a higher value, then I can show even better characteristics. So this is the critical speed for field line at, say, R1. I may say this is R1, so this is omega 1. Maybe this is R2, and let me call this as R1F, R2F. I am talking about resistance of the field, so I am writing R1F and R2F and so on. This omega 2 will be the critical speed for R2F. This is how it will be. So I am going to have basically, a critical speed defined for a given value of field resistance. Similarly, critical field resistance defined for a particular value of speed. So I would be able to do both in a field circuit, but in general, we drive the generator at rated speed, whatever is given as the rated speed. So for that, whatever we are defining as the critical resistance of the field circuit,
that we say as the critical field resistance for that particular generator with that particular rated speed. As simple as that, right? So much so for self-excitation process in a shunt generator. Let us try to look at the external characteristics for a shunt generator. So let's say I am taking up the circuit of a self-excited generator, shunt, right? And I'm going to take this as the load. So now I'm connecting the load as well. Please note that I will have an internal resistance of RA. Very clearly I'm going to have the field circuit resistance RF. I can definitely include an external resistance RF external if I want, provided I want to control the field maybe beneath whatever is the normal value of field current that will flow. Because if I include an external resistance, the field current will come down. So if I want to reduce the voltage for some reason, then I might have to include an external resistance in the field circuit so that I get less and less value of field current. I'm talking about this with respect to the inherent value of field resistance. I'm not included any external resistance. So I am going to have basically EG as the generated EMF without any IA-RA drop. If I don't have any IA-RA drop, I am driving the machine at rated speed. It will ultimately settle down at the point EG where the resistance line will intersect with OCC. Both of them are intersecting with each other and I get the operating point somewhat like this. Let's go to the first one. So we said this is the operating point. What we get is the intersection between the OCC and the field line. Both of them are essentially intersecting with each other to give me that point. So let me call this as EG rated. When I am driving the machine at rated speed and it has gone on with inherent field resistance and it has finally settled at the point which is corresponding to some value EG, which I call as EG rated. So I would say that now I have allowed the machine to reach its own operating point, because of which we have reached EG rated. Now I am going to connect the load. This may be a variable load, but let us say I am actually connecting it corresponding to a current that will be drawn, which is IL rated. For example, let us take our regular rating, 2.2 kilowatt, 220 volts DC generator. Please note, what is given as 220 volts is generally the terminal voltage. We don't know about the internal voltage. It is going to be very difficult for me to measure the internal voltage because hardly ever I will run a generator without a load. Why would I? I will not. I will always connect a load. So the 220 volts, what is given is normally under the condition of full load. What is the terminal voltage? So we are looking at the terminal voltage as 220 volts. 2.2 kilowatt is the output. We are going to have an output in the DC generator, which is an electrical output. That is going to be 2.2 kilowatt. So in which case, I can right away say 2200 divided by 220 is going to be the load current. It is DC, no power factor. So I can directly calculate basically the current as 10 ampere. So basically I am going to have a current of 10 ampere flowing through this. Even if I assume probably that RA is 0.1 ohm, very, very small, still I am going to have at least 1 volt drop as IA-RA drop. So what originally the machine would have generated would have been maybe 221 volts, out of which 1 volt is dropped and I am getting 220 as the terminal voltage. So based on this, I should be able to write the equation somewhat like this. If I say this voltage is VT, I am going to have VT equal to EG minus IA-RA. Right? Because internally whatever is the drop that is happening within the armature, Devoid of that, whatever is available, that is what comes out as the terminal voltage. And similarly, I should be able to write Vt divided by Rf equal to If. And I can say also Vt equal to VL, which is also equal to IL times RL, if I am assuming I am connecting a resistance load. Right? So I can simply say it is IL times RL. Instead, I could have connected a motor. The generator could be feeding a motor. But right now, I am just taking a passive load, which is a resistance load. Right? Apart from this, if I say this is IA, this is what is supplying actually the field current as well as the load current. There is no other source. So obviously, my generator has to supply both of them. That's why I call it as a self-excited generator. So this is plus and this is minus, which is working like a voltage source. So I'm going to have IA equal to IF plus IL. This is going to be my armature current. Right? So basically we are writing KCL. That's all. Nothing more than that. So these are the equations which govern the operation of the shunt excited DC generator. All of them put together, they are going to govern the operation of a shunt excited DC generator. Of course, we have the fundamental equation what we initially derived, Eg equal to K phi omega, which is actually equal to K dash multiplied by IF multiplied by omega. If I assume in that particular operating point, phi is equal to some constant multiplied by IF at that particular operating point. And I'm going to also write, if I look at what is the torque, electromagnetic torque, which will be generated within the generator, which is actually a counter torque, right? So this counter torque is going to be some K phi multiplied by IA. So both these equations are very much valid, whether it is a generator or a motor. Only thing we will say in a motor, we will call this EG, not as EG, we will call that as EB, back EMF or counter EMF. And we will call basically the torque as the electromagnetic torque, which becomes the output torque in the case of a motor, whereas it is a counter torque in the case of a generator. That's all is the difference, right? Now, let's try to draw the external characteristics for this self-excited generator. So, let me draw first of all what we drew as the OCC, because from which we are going to derive how the external characteristics look like. So, this is my EG, this is going to be IF. So, I'm probably going to have this as my OCC, right? And let me probably look at the resistance line somewhat like this. So this is going to be the IF RF characteristics. I'm showing very, very small margin, so we may not be able to really load the generator much, but nevertheless, let us try to probably look at how we are going to go about drawing the external characteristics. So let me probably take another X and Y axis where I'm going to draw the external characteristics. When I draw the external characteristics, I'm going to look at the terminals basically. So which means I am more concerned about the load. So I have to look at how much is the load current in one sense, and I have to look at how much is the voltage that is available, which is Vt or VL in another sense. That's it. Okay? So let me look at first of all under no load condition. So this is the operating point. So let me take probably this as the starting point of my characteristics, which is actually maybe Vt1 at IL equal to 0. Right? Now, if I look at another voltage, maybe I just want to look at this voltage, right? So I'm going to take this as the voltage which is being, taken off to the external characteristics. So let me call this voltage as VT2. At this point, if I look at it, this is the generated voltage. This is the load resistance, field resistance line. So this is the only margin I have. So if I may call this as the margin, PQ is the margin I have. Are you getting my point? Because whatever is available, this is basically the margin what I have in terms of building up the field current even earlier. So I should say this corresponds to actually the IA-RA drop. So if I assume roughly IA and IL are equal, they are not. Definitely IA is IL plus IF, but it's very difficult for us to every time subtract IF, otherwise you have to directly subtract IF as well. I know what is the armature resistance, so I should be able to get what is my IA because I know this PQ length. So PQ is actually IA-RA at VT2 terminal voltage. So I am going to essentially get this PQ divided by RA is going to be IA, which I am approximately assuming it to be IL. I can assume IA equal to IL invariably because RA is going to be really small most of the times. That is going to be only 0.1, 0.2, whereas the field resistance is going to be 150 ohms, 200 ohms and so on. So if I look at normally 22 kilowatt generator, I will probably have hundreds of amperes of current through the armature, but I will have only 1 or 2 amperes of current through the field, which I can afford to ignore if I am talking about full load condition, for example. So roughly I am ignoring, because of which I should be able to get, let me call this as maybe IA2. So I have to look for where IA2 is, and probably this is one of the points which is corresponding to IA2 comma VT2. Similarly, I can take the third point. Maybe let me take the third point here. Right? What I have is now this much as the leverage. What I have is this much as the leverage. So that corresponds to the IA-RA drop. So I'm going to have essentially this as the IA-RA drop, and I'm going to have basically this IA-RA drop. If I try to get this as RS, so I'm going to have RS divided by whatever is my RA, this will be maybe IA3. So I'm going to have maybe slightly higher current or whatever. So I have to essentially derive point by point, and then I should be able to basically get, so this was my second point, this was my third point, maybe my external characteristics will be somewhat like this, and finally it may end up under short circuit condition. If I just short circuit the load terminals, voltage will be 0. If the voltage is 0, that means I am not getting any terminal voltage at all. But maybe there is some internally generated voltage for sure. So corresponding to the internally generated voltage, I will have IA-RA equal to EG. That's all I will get. And because it is IA-RA equal to EG, I am getting 0 voltage as the terminal voltage, because EG minus IA-RA will be IA-RA minus IA-RA, which will be 0 volts. So this is my short circuit condition. So whenever I have a short circuit condition, I can probably end up in that inadvertently, not intentionally, maybe by some chance it has become a short circuit. Despite being under short circuit condition, I am going to have automatically the generator protected against over current. The currents will not be extremely large. In a transformer we said, if we short circuit, we are going to get 40 times, maybe 30 times the rated current. That cannot happen in self-excited generator because the field current also depends upon the terminal voltage. The moment I short circuit the generator, the terminal voltage will become 0. Because the terminal voltage becomes 0, I am going to have very clearly, the current limited by the fact that the field current itself has now become 0. If I actually have two parallel paths, on one side I have 150 ohm resistance, which is actually the field resistance, and on the other side I have short circuited. Where will the current go? All the current will go here. No current here, so IF will be equal to 0. So if IF is equal to 0, automatically I have come back to the residual magnetism voltage, nothing better than that. I'm not going to get anything more than residual magnetism voltage. So the current I get depends now upon what is the residual magnetism and what is the value of armature resistance. So I'm going to have Eg, which is generated with respect to residual magnetism, divided by Ra, which is the inherent armature resistance. And that is going to give me definitely not a very large current. It is going to be smaller current, which will automatically protect my machine against any short circuit condition. So self-excited generators normally have this major advantage that inadvertently, if there is a short circuit across the terminals of the generator, automatically it will be protected against any overcurrent, because the overcurrent will be still limited by whatever is the voltage that is generated only due to residual magnetism. Right? So this is one of the major advantages of self-excited generator. Nevertheless, in separately excited generator, invariably we have a complete control over the field, which allows me to probably build up the voltage quite easily, whereas in self-excited generator I am limited by critical speed, I am limited by critical resistance of the field, and so on and so forth. I don't have a complete control over the field current. That is going to be one of the negative sides of self-excited generator. But self-excited generator is quite commonly used because of the fact that I don't need a separate excitation source. Wherever DC generator may be needed, it is easier to use a self-excited generator rather than separately excited generator. So when we conduct the experiment on the laboratory, little bit of introduction I'll give you for that. What you will have is basically a DC generator, maybe separately excited DC generator. This is generally connected to multiple number of motors. We have on one shaft 2 DC machines, 1 synchronous machine and 1 induction machine, all of them connected, in one shaft. So only one shaft, when it is rotating, all the 4 machines will be rotating simultaneously. So if I have one of the machines even working as a motor, as a prime mover, which is imparting mechanical power, it is good enough. So I'm going to have maybe an induction motor working as a prime mover, maybe a DC motor working as a prime mover, and then I'm going to give a speed of omega, which will be rated speed. Right? So this will be run at rated speed, and I'll make sure that this field current is controllable. If I have to have the field current as controllable, generally what I would do is to connect a potential divider, preferably. So if this is my potential divider, I will connect here this variable point, I will connect to one of the movable points. So I'm going to apply basically plus minus maybe 220 volts DC, for example. So if I bring down this voltage to 0, right, hardly any resistance included in the position, I will get literally 0 current going through the field circuit. So what is the voltage that will be generated will be residual magnetism voltage, nothing more than that. So what I would do is to put a DC, so I'm going to put a DC voltmeter here, and I will also put a DC ammeter here, and I will put a load which is variable. This is how it will be connected, and I am assuming that this is plus and this is minus of the generator. Right? So initially for OCC, I will have basically, if I put a switch here, I can open the switch, no problem. Right? I have a switch here, I can open the switch. So it will be on OCC, I can slowly increase the field, and then I can look at what is the voltage generated at rated speed. So I'll get completely the entire characteristics, which is OCC. Until I reach the rated value of voltage, I would not definitely overload the machine beyond that. If it is rated for 220, I would like to go until 220 and then see that I stop there. Right? That's what we do for OCC. For the load characteristics, now I'll close this switch. So this will be closed, and after closing the switch, I have kept the excitation at rated value. I have kept the speed at rated value. Now I have to slowly vary the load, note down what is the terminal voltage versus load current. That's about it. So that tells me really what is the internal drop that is taking place. Right? So this is essentially for how to experiment on a DC generator. Right? Just to add on to this point, I should say there are compound generators. So we have looked at separately excited generator, we have looked at shunt generator, we are yet to look at compound generator. So in a compound generator, I am going to have basically a series field as well as shunt field. So I have a shunt field and series field, and I will connect the load here. This, what I have shown, is a long shunt connection, as I mentioned maybe 2-3 classes ago. Short shunt is only across the armature. It will be connected only across the armature. So let me draw the short shunt as well. So I'm going to have only across the armature I have this connected, and then I'm going to have the series field along with the load as well. Please note, in short shunt, I'm not going to have any series field current at all if the load is open. So under open circuited condition, I will not have any series field current. Whereas in long shunt, I will have, even if the load is open circuited, I'll have a small current which is field current, but field current is generally very, very small, because of which I can ignore it. Series field influence on the overall main field will be negligibly small when there is no load. So under open circuit condition, in general, I can say under open circuit condition, series field influence can be ignored. So I don't have to really look at the series field influence at all, because I'm not going to have any perceptible or perceivable current through the series field. It is going to be really, really small, whether it is long shunt. In short shunt anyway, it is going to be 0. So I should say, in general, the series field will be directly affected by the load. If the load increases, I'm going to have the series field current increasing. If the load is decreasing, the series field current is going to decrease. That's why we said generally, you can say, in general, the series field is called a series field because it is in series with the armature and it's going to carry the same current, roughly the same current as that of the armature current. Of course, in this case, you can say the series field is going to carry only the load current, whereas in this case, it is going to carry the armature current, right? So I'm going to have basically armature current coming up here, whereas I'm going to have here only the load current coming up. So we are going to have basically the current going like this. Now, If I have the series field aiding the shunt field, both of them are additive. What I mean is, I have some series field flux created, shunt field flux also created. Both of them are aiding each other. So if I look at the total main field flux, the main field flux is addition of the series field flux plus shunt field flux. So if I have phi total equal to phi of the field plus phi of the series field. What I mean is, this is shunt field, of course. Phi of shunt field and phi of series field. Then I'm going to have, as the load increases, I'm going to have more and more flux coming up. What we drew as the external characteristics for the separately excited generator, for example, we said that we will have a drop like this. Originally, if the generator had been ideal, I would have had constant voltage. But it is not really ideal, because of which I'm going to have a drop in the terminal voltage. Right? And this drop we said is roughly IARA drop. Of course, there will be some armature reaction drop. Currently, I am not considering. I am only looking at IARA drop. If I am able to compensate for this IARA drop by providing adequate amount of series field, then I will get a flat characteristics as far as the voltage is concerned. If I am going to have enough amount of series field influence on the overall field to compensate for the IARA drop, I will get almost a flat characteristics irrespective of the increase in the load current. That kind of a generator is known as level compounded generator. So I will have level compounded generator if I am going to have whatever is the IARA drop, this is compensated by increase in the series field. Whatever is the increase in the series field, if it is compensating for the IARA drop, then I can say the voltage, the terminal voltage is going to be almost a constant. If I have some series field influence, but it is not good enough to compensate for IARA drop. Let us say IARA drop is 10 volts, whereas the series field voltage generated is only 8 volts or 7 volts. Then I am still going to see a drop, and maybe the characteristic will lie somewhere in between the two. Right? So the series field influence is not good enough to completely compensate for IARA drop, but it is partially compensating. Then we are calling that as under-compounded generator. I am not really providing the complete compensation for the IARA drop. I am only providing partial compensation. So I would call this as under-compounded. This is just the separately excited or shunt. Right? This is roughly the level compounded. If I say roughly I am getting a flat voltage, flat compounded or level compounded. Some people use it as flat compounded also because it is a flat characteristics, horizontal characteristics. If I provide more amount of series field compensation than the IARA drop, as I load the generator more and more, I will see a steady increase in the voltage as long as the saturation does not interfere. So I may have actually the voltage slowly increasing. That is essentially known as the over-compounded. Under-compounded is less amount of compensation given. Over-compounded is more amount of compensation given. and level compounded or flat compounded is just sufficient amount of compensation given. So this we will call as over compounded. So in all these cases, please note that the total flux what I am getting after I pass the current through the series field also is more than the original shunt field flux. So I'm going to have the total flux greater than whatever was the original shunt field flux. So this is actually added cumulatively. So we call this as cumulatively compounded generator in general. So cumulatively compounded generator refers to where the series field and the shunt field aid each other. If both of them aid each other, I'm going to call that as cumulatively compounded. So under cumulatively compounded, I have three configurations. One is level or flat. The second one is under compounding. The third one is over compounding. Right? So obviously, if I am specifically mentioning about cumulatively compounded, there should be maybe another configuration where they will oppose each other. So I have one more configuration which is actually phi total is going to be phi shunt minus phi series. So you bring down the voltage drastically. Whenever I load the generator, the voltage is going to drop pretty drastically. Not only IARA drop is depleting the voltage, but the series field is also trying to deplete the main field itself, because of which I'm going to have lower and lower voltages. So if I draw the characteristics, let me draw it once again. I am looking at VT versus load current. And if I draw for level compounded, I'm going to draw it like this. If I draw it for over compounded, I'm going to draw it like this. If I draw for under compounded, maybe I'm going to draw it like this. Right? And if I am drawing for differentially compounded DC generator, literally it will reach zero voltage, when I load it to the fullest extent. So this is differential. These are all cumulative, with this being under compounding, this is over compounding, this is level compounding, and somewhere in between I should draw the normal shunt. Just shunt alone, no series. Yes.
Earlier you told that the total flux will be added by shunt and series.
That is cumulative. All of them correspond to cumulative. Cumulative is the condition where the series field and shunt field are added together to give me the total flux. This is another type. So I have basically, if you look at the DC generator configuration, I can say, of course, one is separately excited. We have seen that already. And the second one is shunt. The third one we called was compound. So inside compound generator, I can have long shunt and short shunt. This is depending upon the connection. Right? But in this itself, I would say there are two. One is cumulative. The other one is differential. Under cumulative, I talked about three. One was under compounding. The next one is level. The third one is over compounded. Right? Is this clear? Right? So, with this, we are completing basically our discussion on the compound generators. One small topic that is left over is the series generator, after which we will branch over to motors. In motors also we have all these classifications. Now that we have understood generator, hopefully motor should be simpler. So we'll look at motors, and then at the end of motors, I'll discuss commutation in really great detail. So with that, we'll conclude our discussion on DC machines itself after looking at the speed control, braking, everything for the motor. Okay?